Many thanks for the invitation to come here this afternoon and to talk about my joy of discovery. I also would like to acknowledge the Royal Academy for making this possible, and of course Novo Nordisk. I have very good memories because Novo Nordisk supplied us with an enzyme many years ago, and one of my PhD students, the girl in my group at that time, was struggling a little bit with a chemical conversion, a catalysis, and the enzyme, Novozyme, saved our project and it worked beautiful. Thank you so much, and I know you are sponsoring this event. Thank you for more than one opportunity. So I will definitely talk about molecular motors, but I would like to put it also a little bit more in perspective of what made us enthusiastic about this field of science and what led me to the stage where we are now. And I will include some very recent example of what we are doing. So let me go back in time a little bit. This, you all remember this gentleman here, the Wright brothers, who were the first mankind flying with an artificial machine. And I often get the question, why do we need molecular motors on machines? You know what they were asking to the Wright brothers? Why do we need to fly? If God wanted us to fly, He would have given us wings. Nobody would have predicted that 100 years later we would have a Boeing 747 or an Airbus flying at 1,000 kilometers an hour, 10,000 miles across the ocean, carrying 400 people. Although we admire the flying bird, I mean, it's fantastic, Mother Nature. But you know, this is not a flying bird. The 3.5 million parts are completely artificial, and the flying principle, ladies and gentlemen, of a Boeing or an Airbus is not the flying principle of a bird. Try to carry 400 people at 1,000 kilometers an hour across the ocean. You will fail. But we should also be modest, because 100 years after the Wright brothers, we cannot build a bird. I challenge my biology colleagues, they cannot build a single cell of the bird. They cannot build even one of the machineries of the single cell of the bird. So there is still a lot to be learned. Of course, we should not forget that the basis of our research is fundamental science. And nowadays, I don't know about Denmark, but in many countries, fundamental science is a bit under pressure. We should not forget what fundamental scientific discoveries, new insights, etc. were needed to make this happen. My students cannot imagine that there was a world without smartphones. It has completely changed our world. But we should not forget that it was a 50-year route to change the world, because it was physics and chemistry who made the transistors, the liquid crystal materials for the displays, etc. in the 40s and 50s of the past century. Nobody knew that we would invent a smartphone. These were fundamental discoveries in natural sciences. And of course it took physics, chemistry, engineers, computer scientists, etc. to make 50 years later a smartphone that has completely changed indeed the way we communicate with each other. We built on a fundamental science basis. And then we need many disciplines to make this possible. So the joy of discovery is a route into the unknown. And of course, when we write a grant application or we think about what to discover, we look at the part and we have an idea. But we should not forget that it's about questions. Which questions are we going to ask? Which scientific questions? And so we provide challenges for our young students, dreams for the people, opportunities for our society and industry. It's indeed an adventure in the unknown. And more than often, we get simply lost in this beautiful garden, which is called the garden of science. And of course, in my case, it's the beauty of the molecular world that I enjoy so much. And what we get lost, we get up to question marks that we have never thought about. These are often the most beautiful questions and lead to the most significant and marvelous discoveries for the future of our society. So don't be afraid to get lost in the beautiful world of knowledge and science. I am from the north of the Netherlands. You see, here is Denmark, Copenhagen. I'm from the north. Here is Amsterdam. There is the city of Groningen. It's more than 1,000 years old, and it's a typical university town. It's dominated by students. and we used to live outside the town. I grew up in the north of Holland, on the east part here, and this is my parents. I grew up on a farm. And people ask me all the time, how is it that you became a scientist? You know, I didn't know when I was a small kid on the farm. I was the second of a family of 10 children, and I wanted to become a farmer, I think, as a small boy. But my father said, you better study first, and then we will see again. I got a lot of inspiration from my parents, and on the farm there is plenty to discover. We lived in a very remote area, and I was debating with my father, for instance, how is it possible that from this tiny seed you can grow a corn? Why is this flour red and why is this potatoes white? There's so many things to discover, you know. And then I was lucky that I had excellent teachers. This was my chemistry teacher in gymnasium, in high school. And although mathematics was my best topic, the fact that he did with us experiments, he made us so excited about natural sciences. I choose chemistry, you know, the fact that you can smell something, you can make a beautiful color, all these fine crystals. So I saw him last year at a reunion of our school, and he said, I wish every child at least one good teacher. That makes the difference. And I'm sure you all remember at least one good teacher. Then I went to the University of Groningen. This is the main building. This was my professor Hans Winberg, who was educated in the United States. And he put the bar pretty high. And this was, I think, one of my first molecules which I made because I got really engaged in synthetic chemistry, building my own molecular world. And one of my first molecules, and I came to his office, and he said, nobody has ever made this molecule in the world, not even in America. It was an absolutely useless molecule, but it made me so proud that I had made something that I had, like your first poem or so, or a piece of music or whatever. And so I want to give credit to our teachers, because I think we should not underestimate how important it is that teachers open windows and shape the future with our young talents, and we should encourage them. So after my university studies, I went to work for Shell. I didn't do a postdoc, but I went to work for the Shell, the Mixed Shell Research Laboratories in Amsterdam, working in catalysis. And then later I went to the Biosciences Center in England. But then I decided to go back to the university because I wanted to work with students and build my own research group and work on my own ideas. So in the art of building small, I do chemical synthesis. That's the core of my activities. Building molecules in the laboratory, new molecules, new materials, like this one, for instance, which we actually built to test a bonding theory. Not because it had a special use, but sometimes you make something because it's simply you test a certain theory. Now this turned out also to be a catalyst, by the way, but I thought it was a beautiful molecule because of the symmetry of the molecule. Then you ask me, what is a beautiful molecule? I ask you, what is a beautiful painting? So a passion for molecules, designing my own molecular world with our students. That is what we are doing. But let me go back once more in time, and that is to this gentleman, Dmitri Mendeleev, because in 1869, he proposed the periodic table of the elements. And this year, the UNESCO declared the year of the periodic table because it's 150 years ago. We celebrate. And so Mendeleev proposed the periodic table, and it connects all the atoms and molecules in the entire universe and in your body, of course, and every material around us. So I would say the fact that we have the periodic table is quite an accomplishment and makes it possible that we can make all these things and we understand your own body, at least to some extent. Mendeleev, in my opinion, easily ranks among the Newtons and the Einsteins, and I should probably also put Niels Bohr here. I mean, our heroes of science that have laid the foundation for the sciences as we know it today. So we know now how to build molecules, thanks to this. We also know how our own body looks, you know. This is the molecular formula of your body. Look, hydrogen 375 million, oxygen 132 million, carbon 85 million. One cobalt. It's very sad, eh? Only one cobalt. You see, there is a lot of elements, you know. I couldn't even put all the elements of the periodic table here. Why is there so much hydrogen and oxygen? Because 60+% of your body is water. Can you imagine? Our president here, he looks pretty okay, no? More than 60% is water. Isn't it marvelous? Mother Nature is fantastic, no? So this is your smartphone. These are all the elements in the smartphone to make it possible that we have a smartphone. Sometimes we forget that you need materials and components, to make a smartphone. These are all half the periodic table almost. So we built these in the laboratory with our students, and I want to emphasize, especially today, that we share a universal language. That is the language of science. And for chemistry, we have the language of the molecules and the atoms. And when I go to China, I don't speak Chinese, but when I go to China or Japan or South Africa or America or to Denmark, we all understand that this is sugar, because we have a common language in science. And this makes us that we have no borders. We should not forget. These days there is a lot of talk about borders. I'm not in politics, sorry. But scientists go beyond frontiers in unknown territory, and we don't like borders. We want to go beyond borders. We have international cooperation, and we have shared a passion for discovery. And I think these are values that we like a lot and we share with our young people. So we can build small molecules, 2 carbons and 4 hydrogens, which is ethylene. It's the basis for one of the most important plastics, polyethylene, 160 million tons a year. We can discuss later if this is wise that we do this, but it helped us a lot to build a modern society. We also built very complex molecules. Vitamin B12, I would say this is as essential for your body or for our life than ethylene. Carbon, hydrogen, nitrogen, oxygen, phosphorus, cobalt. Vitamin B12, you need only tiny amounts, microgram quantities to stay healthy. So the whole world prediction, as far as I know, is 35 tons a year. Simple and complex, huge scale, big industries, or small scale, very precise design, in this case a pharmaceutical. So we build the cables and the cars, all the components of your cars, drugs and dyes, soaps, all the components of your smartphone, all the materials. Of course, not in isolation. These are different expertises coming together. Chemists, biologists, physics, pharmacy, engineers, computer scientists, etc. This is what we can do. But what we are not very good at is making something that moves. Look, when I move here, I talk, and it was mentioned already by the president, this is all these machines in your body that make that possible. And you will say, machines, I know that. Our planes, our trains, our cars, our robots in our factory, etc. My dishwasher. The rotary motors in your body, look, there's real rotary motors. The bio-nanomotors that make it possible that things are transported in your body from one place to the other. The ribosome, which is probably the most fantastic robot that you can think of. Much nicer than the robot, or complex than the robot in a car manufacturing plant, the robot that builds your cars. This builds the majority of the proteins in your body. The bacteria flagella motor. Look, the bacteria that swim in your guts now, that have this beautiful rotary motor that make it possible that they can swim. They can go forward, they can go backward. Isn't it fantastic? Optical switching, the information process in your eye. The fact that I can see you and you can see me. So, we are working at the level of molecules, which is at the nanoscale. And this is all part of molecular nanotechnology. And it was Richard Feynman, one of the most famous physics persons, who said in 1959 there's plenty of room at the bottom. And he didn't mean go to the basement. What he meant is, at that time, going smaller and smaller and smaller, and work like Mother Nature does by building with small molecules and making nanostructures, etc. Because we all know the first computer that was built, I think by IBM, it filled almost half this room and could do way less than your smartphone. And then the devices became smaller and smaller and smaller, and we are now at 10 nanometer, 12 nanometer dimensions or so in the latest chips. This is top down, but bottom up means trying to build with molecules, atoms, etc. And it took 50 years, and indeed 50 years later we could build tiny machine-like functions. And this is Jean-Pierre Sauvage of Fraser Stoddart, where I had the privilege to go to Stockholm a few years ago. So just to put it in perspective, 1 nanometer is 1 billionth of a meter. So the cross-section of a hair, you see, I take here one hair. You can see it, one hair. The cross-section of this hair is really huge for us. 80,000 nanometer. My molecules are 1, 2 nanometer. Does size matter? Yes. When you go to a sandy beach here in Denmark, you fall on this beach on a day like today with a lot of sunshine, you don't care. It's beautiful. It's very soft. But when you go to a pebble beach in the Mediterranean, you are careful because it hurts. And when there is a pebble in your bathsuit, you take it out. But when you come back from your beach here in Denmark and it has been a bit windy, and I know there is a lot of wind like in the north of Holland, you find this fine sand everywhere. It's only difference in size. It's the same material. So a lot of the nanotechnology that if you have seen in products so far is about sizes. Nanoparticles, for instance, in nanosensitive, this very nice cream. It's really beautiful. It feels so good. It's really simply because the particles are so small. You have to pay also quite a bit. Quantum dots, look, 6 nanometer, 2 nanometer. You get this high definition color TV screens. This is all to do with size. And this is hard materials. What I'm talking about is about soft materials, like the materials in your body, the molecular materials. Of course, people ask all the time, how can you see, you cannot use an ordinary microscope, of course, because micro, it says micro, 10,000 times larger. We are at a nanoscale. But of course, people have discovered new microscopes. For instance, like this scanning probe microscope, where you have a tip and it ends in one atom, and you can scan the surface, and you can even write letters on the surface with atoms and molecules. This was done by IBM. And so on the cross-section of the human hair, I think you can write the whole library of maybe of this medical school here on the cross-section of a human hair. 250 million letters. So let me talk a little bit about switches, and then I will continue with motors. Because this is where we started. And so when I started my independent career, I came back from Shell. I had to start some programs, and I had this idea, can we do information storage computing at the molecular scale? Now, the most beautiful system is, of course, in your eye. Look, in your eye, there is this switch that makes it possible that you can see me and I can see you. This is called retinol, and it's just switching from this form to this form. It's a small molecule, 1 nanometer, and it switches from a band state to a linear state. The only thing what happens is when light comes to your eye, it excites the molecule, so you put in energy, and it rotates from this state to this state. It changes shape. And that makes it possible that we can see. Can you imagine? How beautiful. Not with one molecule, Millions and millions of these in your eye. Switches at the nanoscale. 1 billionth of a meter in size. Now you all know what a switch is. When you switch on your car, you switch on the light. This is also a switch. But a switch means it has to go back and forth. 0, 1, 0, 1. Because if it switches, you see light comes to your eye and it switches only in this direction, I would see you only once and then it would be over. It has to go back. And this is what happens in your eye. So we had to build that, and then you might ask, oh, this is nice, 0, 1, 0, 1. Why don't you use that material from your eye? But of course, when you take it outside the natural environment, outside the biological system, you cannot build a computer or a device with it because these are way too sensitive. So we had to make very robust molecules, and we built molecules that were so stable that we could switch back and forth many times. So this is the natural system in the eye, this is the artificial system. And how did I came to that? This was probably 7, 8 years after my PhD, and suddenly I remembered indeed that we had made these special molecules during my PhD that were active to light, and when we studied them, they turned out to be really very suitable for this purpose. So we modified them a little bit, we re-engineered more or less the molecules, but we remembered the molecule of my PhD study, and nobody had used them, and they were very useful for this purpose. And so this is how it all started. And then we built information storage systems. Here what you see is a molecular information storage or an electronic device. Each of these islands is composed of molecules, layers of molecules that you can switch, 0, 1, 0, 1. You can write information. So we worked also together with companies, to write information in a piece of plastic, zeros and ones. And so you can build a compact disk, and then you can calculate how much information you can store on one compact disk. And this is the number of megabytes, you see? That means one CD, and you can play 240 years music. That is to say, your grandparents and your grandchildren, 6 generations, can play constantly music with one compact disc without changing. This is killing for the music industry, of course. But this is the potential of nanotechnology, if you can write zeros and ones at the molecular scale. This has unfortunately not been realized. We can write zeros and ones, ladies and gentlemen, no problem. We can detect them also. But then at the nanoscale, we have one molecule here, and we have one outside the building at the nanoscale. Because if they are so densely packed, we don't know exactly how to address them. That's still a problem. And I hope there are some smart students here that help me to come up with a solution. So, yes, this is the potential, and this was the start for a big program on information storage, molecular switches. But I want to share with you a very recent development, and that is how to make smart drugs. Because we thought, if you can make switches, can you make a drug, a pharmaceutical, that you can switch on and off? So here you see what you don't like when you go to the doctor, that the doctor gives you an inactive material, an inactive pill. If you go to the doctor and you want to have something to relieve pain or so, you want to have a compound that is active. But we want them inactive. That is to say that we can switch it on actively, exactly there where it's needed. Smart, high precision therapeutic action. What we do is you take a pill, you build in a switch, you irradiate. For instance, you have an infection here, you take this pill, it doesn't do anything to the rest of your body. You switch it on exactly on the spot with a flash of light. That's the idea. We work on 2 areas, among others. One is bacterial resistance, which was called by the World Health Organization one of humanity's ticking time bombs. You all know the real problems because there's hardly any new antibiotics coming to the market. Infectious disease is a real problem. And they expect, why is that? Because of the overuse of antibiotics, the resistance build up. And they expect that this is going to be a real problem in the future. Several millions of people will be killed if we don't do something. So can we make antibiotics that we can switch off and automatically switch off after a while and don't build up resistance? Or cancer treatment. We all know the problems with cancer treatment when you get chemotherapy, that you get all kinds of nasty side effects. I don't have to tell you. My dream is that with these new imaging techniques that we develop in several groups around the world, together with the people in the medical schools, that you find these tiny tumors, and then you take this chemotherapeutic agent. It doesn't harm the rest of your body. You just write the activity. You activate it on the spot, there where it's needed. High precision therapeutic action. That's still a dream, eh? It's still very fundamental research. So yes, what we did is we took an antibiotic, Cypro, which is used here also in the hospital. We built in a light switch. We switch it on and off with light. And the nice thing is that this form, you remember, the shape changes. This is inactive. It is not an antibiotic. This is an antibiotic. It acts as the normal antibiotic, more or less. But due to the fact that this is not so stable, it also switches back automatically. And we can precisely establish if it switches back in an hour, in 5 hours, in 24 hours, or in 48 hours. And so we made it so that after 6 hours, the activity is gone, the bacteria grow normal. Or after 24 hours, it leaves the body, bacteria grow normal. No antibiotic anymore, no bacterial resistance build up. That is the dream. This is what we could realize with cells in the laboratory. This is still far from the clinic, of course. But you can see we can grow. This is typically what we do with cell growth. Every biologist does this. You grow cells in a Petri dish. This is a yin-yang figure that my students made by putting a mask. Here it is covered, and here it's open to the light. when you irradiate with light, you activate and you see bacteria don't grow. We used it also for chemotherapy. This is botazomic. It's used in the clinic. We put in a switch, and we can switch on and off to some extent the proteasome inhibition in this case, which is very prominent in anti-tumor chemotherapy. Once again, this is all laboratory work. Yeah? The only thing we have done is with cells in the laboratories. We have not worked in the clinic yet, but we are cooperating heavily with people in the medical school now to make these smart drugs for the future. And now, certainly in the last 3, 4, 5 years, a whole community around the world is working on this kind of approaches. There's one major issue, and that is how to get light in your body. And so, you have, this is the spectrum, This is your body, and you have to between 600 and 900 nanometers. You all know that red light, blue light is dangerous, That's why you take a sun cream when you go to the beach. But red light is no problem. You have your red laser, you can go straight through your finger. That's not possible this one because this is a green one. But red light can go centimeters deep. And you know infrared light, heat, goes deep in your body, No problem, it's harmless. So we had to build that, and it took a couple of years, and now we have for the first time built switches that we can switch on and off antibiotic activity with red light. And we use it now for many other applications. And now my students do the first experiments with small animals, to make the next stage to hopefully in the future towards the clinic. It's also very nice that your students get recognition. This is with the smart antibiotics. These are the hands of the student. This is the hand of the student who did this work and made the discovery. You see it here again. There was a whole group of famous photographers was invited to go to research laboratories. They were in Cambridge and Harvard, etc. They had read this paper, and they visited also our laboratory. And they made several beautiful photographs, including the hands of my students. And you see the red light, and it was in a big exhibitions in several places. This is the one in Groningen I copied here. But I put this on purpose here because arts and sciences have something in common, of course. And most importantly, maybe imagination and creativity. Come up with unconventional ideas. And enjoy the beauty of science like we enjoy the beauty of art. So, to summarize this part, the bio-nano future, will we have roving nano-robots that go through your body? I will come back to that later. DNA nanotechnology, this is a hot topic, Editing DNA. You read it in the newspapers last year, that the first experiments have been done with cells. Network complexity. This is not the metro of Paris or London, This is just a tiny part of your biological network. When I cut my finger, I had a cut in my finger here, you see? The blood clotting, that the blood can clot, become stiff, that you don't bleed to death, is due to this 80 integrated chemical reactions. It's just a tiny part of your complex machinery. I talked about photopharmacology, how to make smart drugs, imaging techniques, rewiring the brain. That's another interesting area for the future. Now we get a lot more insight into neurobiology, how our brain functions. We can discuss it later. What happens when we get chips implanted in our brain in the future and connect to the internet? Okay, let me continue with molecular motors. I talked so far about switches, and switches go back and forth. But we all know when we have something that moves. When you ask a child what is dead or alive, he says a pebble on the beach is dead, but this animal is alive because it sees it moving. Also this plant, also a human body. But we should also realize that it is a fundamental issue about motion. Sometimes you hear on television or you read in magazines, be in equilibrium, find your equilibrium. Please don't. Find your balance or harmony. That's good. But if you are in equilibrium, you are dead, biologically. We are constantly pushed out of equilibrium thanks to the metabolism and all the machinery that's in our body. Avoid to be in equilibrium. So we have to learn how to do that, to get out of equilibrium. And we do that, for instance, by our molecular machines. This is the most fantastic rotary motor that I know. You might think in your car there is a beautiful motor. I agree, there's a beautiful motor. Depends a bit on which car, but this is by far the most beautiful motor. This is a rotary motor, the ATPase rotary motor in your body, in the cell memory. There are millions and millions of these motors. And just to make, again, an answer to the question, why do we need motors? What does this motor do in your body? Many people probably don't know. I also learned it from my friends in biology. These motors make make the fuels in your body, the ATP. It's a factory to make the fuel in your body. And it makes half your body weight every 24 hours. Can you imagine if you are 80 kilograms that it produces in 24 hours every day, half your body weight, 40 kilograms of fuel? That's a bit strange, eh? You don't eat 40 kilograms. Yeah? But it's all recycled. Most of the material that is recycled by these machines and by the metabolism in your body. Can you imagine almost half your body weight? I often hear, we should do in our society more recycling. Our industries, we ourselves. Come on, guys, why cannot we recycle? We are simply not smart enough. We have to learn it in the future to make it sustainable. Our body recycles half your body weight with these tiny machines. Not with one motor, but with millions of these motors. But this is not my main message. The main message is how to build a motor. And what were the fundamental scientific questions we had to ask? How to control rotary motion, yeah? And how to control left and right. Think again of your car. If there's equal probability going forward or backward, you stand still, eh? You never get anywhere. You have to go either this direction or this direction, clockwise or counterclockwise. That's the crux. That's what you have to invent. And you have to put in fuel, because if there's new fuel, yeah, being it petrol or diesel or electricity, you wouldn't get anywhere either. So how to control motion and how to control left and right in the nano world. And so how to control left and right, we do that by chirality, breaking the symmetry. Like your left hand and your right hand. And we all know that symmetry is beautiful. Look at art, eh? You always see beautiful symmetry elements. Like my 2 ears, and I'm not very symmetric, but when you are beautiful, you are symmetric. In your body, everything is asymmetric. The most prominent examples is the proteins, the amino acids, and the DNA. Look, the right-handed helix of the DNA, where all your information is stored. It was called the Mona Lisa of modern science. How do I break symmetry? These are left and right-handed amino acids, left and right. I learned it already at an early age when I grew up on a farm in the north of Holland, probably also in Denmark. You had these wooden shoes. And I tell you, we all struggle sometimes with left and right. But when as a small kid, you step with the right foot in the left wooden shoe, it hurts so much that for the rest of your life you know the distinction between left and right. You never make a mistake again. So we have to take one of these mirror images and then we can go clockwise or counterclockwise. That's how we did it, and this is how we got our first rotary molecular motor. Actually, it was a bit by accident. And this is typically what happens in science. You do have an idea, you do discoveries by accident, often. And so my students, serendipity it's called. My students built a switch. And then they came to me and said, it does not switch back, but it switches. And I said, come on, that's not possible. And then we were puzzled for 3 weeks, and we did a lot of measurements in the laboratory by different techniques. And then we figured out that it was not switching back, but it was switching forward 2 times. 90 degrees, 90 degrees. 180 degrees, that's half of a circle. We do it twice, you have a 360-degree cycle. This is how it came. And so, you see, it rotates around this axle. It's just the same process as in your eye, but now completely artificial. And you see this carbon-carbon double bond, It's excited by energy from the light. It's a light-powered motor. It rotates. You see the 4 colors. It's 4 different stages, and it goes in one direction. We can make it rotating clockwise. We can make it rotating counterclockwise. If you take this form, it goes left. Take that form, it goes right. Forward and backward. 4 stages, it rotates. This is how it works. You power it with light. That's extremely fast. And then there is a slower step. That's what we call a thermal step. Yeah, by heat. But the step as the switching process in your eye, like this one, is extremely fast. Picoseconds. How fast was this original motor that we built? It was rotating once an hour. And people said to me, come on, this is not very useful. You know, once an hour you cannot build a car. I agree. But we were lucky that it was so slow, because then we saw every step and we could prove that it was indeed going through these 4 steps. If it would have been very fast, we might have completely missed it. Now, meanwhile, in the past 15 years, we have built dozens of different motors. How can you do that? In the laboratory, you can modify your molecules. You can build in different atoms. You can build different bond lengths, different parts in the molecule. You can fine-tune every aspect of such a molecule. And so the fastest one we have now is 10 million rotations per second. And everything in between. Hours, minutes, seconds, milliseconds, 10,000 rotations per second. So this is a kind of a tiny machine that we recently built. You see here it rotates. And you see this part also rotating. But look at this part. It keeps always the same face to this lower part. Look, when it goes around. Do you see that? It's like the moon going around the earth. When you are on the earth and you see the moon, you always see the man on the moon. Yeah? You cannot see the backside of the moon. Eh? This is the same. So this was our attempt towards more complex dynamic functions. This is 1 nanometer in size, 1 billionth of a meter. It's all controlled by light, and it moves, and it has now this machine-like motion. Then my students did the following. This was 6 years after the discovery. They took the material from your display or from your smartphone. And you know, when you look at your smartphone, behind the glass screen, there is this soft material. When you push, you can push. Don't do it too hard, because you push, you destroy your smartphone. There's this soft material. It's called liquid crystal material. And what they did is they took that material, the thin film, and this is the surface of this film. The motor is only 1 nanometer in size, but you don't see it. There's only a tiny amount there, very tiny amount. What they did is they put on top of this soft material, they put a glass rod, you see micrometer dimension, 10,000 times the size of the motor. And then they called me to the lab. I will never forget it, in the afternoon. And they said, Ben, you have to come with us to the lab. We want to show you something. And this was an eureka moment in my whole career. I could not speak for 5 minutes, because what I saw was the following. They showed me, the only thing they did is they switched on the light. And this is what I saw. So you see the whole surface is moving of this soft material. You see the color changes, and you see this tiny boat swimming and rotating, clockwise. We can also make it rotating counterclockwise. This is completely autonomous movements without touching it, just by the power of the light. All driven by the change in this tiny motor, that changes its orientation. So we have now soft surfaces, that can change orientation, that we can use for all kinds of application. And so this was a real eye-opener, because for the first time I saw something really moving. And for the specialist in the audience, this is probably how it works. So this is this tiny motor, and in these liquid crystals you have these rod-like molecules, and they wind and unwind their organization. This is supramolecular change in the surface layer. So now what we have recently done, we use this kind of soft surfaces now with these motors for growing cells on top of it. Because cells, especially stem cells, are very sensitive to surface structure. So we hope we can pursue that. We also build a windmill. You have a lot of these windmills, I know. We have also, I still have some of these windmills here in Holland. And recently last weekend, we had a lot of tourists to see the tulips. We were flooded actually by tourists, but to see the tulips. But we thought, okay, let's build a windmill. You might say, why do these guys, are these guys playing at the university, these professors with their students, you know, doing Lego? And that is appropriate in this country. Well, we play with Lego sometimes. But this is what we did. We put legs on gold, a stator, an axle, and a rotor. And we want to build a tiny windmill powered by light. Just to show that if you have these motors connected to a surface, that they still operate. This is crucial. If you ever want to make a device or so, and think about an electronic device or a storage device for information, you need to integrate. And so this is what we built. We built a nano windmill park. This is the original one in Holland that were made 500 years ago by our ancestors. And this is what we did. 1 billion times smaller. And you see they are all on gold. And we have now a layer, complete layer of these, and they all spin in the same direction. This was not easy to prove. It took us 8 to 10 years, together with our colleagues in physics, etc., to make sure that they were all standing there and they were all propelling. And then you might ask, what is it good for? Of course, this is very fundamental research, but around the world now, many people are working now on responsive surfaces and smart materials. So think about what you will see in the years to come. Self-cleaning windows, because the windows are responsive. Solar panels. This is a serious problem, not in the north of Holland where I live or in Denmark, because we get a lot of rain. But when you are in the south of Spain or the Sahara or in California, they have to clean these solar panels all the time because there's all this dust and the efficiency goes down. Cars that you don't have to wash anymore because they have coatings that are mobile and they can clean because when the sun shines, they get responsive. Not based on our motors probably, because they are too expensive. But once you know the principles, how to make responsive surfaces and coatings, you can easily think about this kind of applications. It will come. Not today, but wait another 10 years. I want to share with you one example of a very recent discovery. And that is making a muscle, an artificial muscle. You know, let me do this experiment with this lady. Can I have your hand? Look, you know, we both use our muscles, eh? And you know why we can do this? Because there are millions and millions of these motors here that make it possible that these filaments contract and we can use our muscles to do this. This is the biology of these muscle functions. Millions of these motors that make these filaments glide. And this is why this guy can jump, he can fly, and this is also quite muscular, as you can see. But what is the key question? How to amplify motion from the nanoscale, the molecular scale, all the way up to the macro scale, so that I can move my arm. I lift my arm or my leg. This was the challenge. And so what we did is we built motors, first of all to get them into water. That was already a big challenge. And then make them like a soap. You all know what a soap is, a detergent. And we make them like a detergent so that they assemble together to form fibers. Here you see these tiny fibers, 5 to 6 nanometer. But that is not a muscle. That was like a gel, like a hair gel. That's what we got. But to make a muscle, they have all to be aligned and to cooperate, to work together. Otherwise, you never get this function. And so we put calcium chloride. And there's plenty of calcium in your body. You all know that, eh? And then this happened. They beautifully align and we get a muscle. Look, here it is. And hopefully my movie works. And this is what we got. This is now a centimeter long, what you see here, a centimeter long freestanding muscle. Oh. And we irradiate with light, I don't touch it, and you see it moves. It moves towards the light, it bends. It can move also in the opposite direction. When you hit with light from the other side. This is what you see moving here, ladies and gentlemen, is an artificial muscle made of tiny molecules that are organized all the way up from the nanoscale to the macro scale. It can lift a piece of paper. It can bend in different directions. Of course, it's not very strong yet, but we show a principle. And what you see moving here, ladies and gentlemen, is 99% water. No, sorry, 95% water, let me not joke. You take this water here, you put in a tiny amount of our molecules, they organize into an artificial muscle, and they can lift a piece of paper. This is where we stand. This is work we have done very recently. Then we were challenged also. I have to tell the story. I got a grant from the Dutch government. And then I had to go to The Hague to tell our Minister of Science and Education what to do with the money, because this is quite a big grant and I had to come up with a challenging project. And I discussed with my students in the lab, and they said, can we not build a solar-powered car? They all can go for 3 weeks or 4 weeks to Australia. They go in this race through the desert, 3,000 kilometers. And I said, no, guys, because this is all done at the engineering schools. These are these engineer students. I don't know if there's also a Danish team involved. They have a good time there. It's absolutely. I said, look, we are not engineers. We are molecular engineers. So we decided to build a molecular car. You see here, 2 meters, 2 nanometers, 1 billion times smaller. It's a 4-wheel drive, you see, and it should drive over the road. Now, of course, you might ask again about playing at the university, what are these professors doing with the students? But of course, the whole idea was, how can we go from rotation to translation, to make moving something? That was the fundamental question. And so we built it. Here is the nano car. And now again, think of your muscles and think about movement at the nano world. That's different from moving a car on the street here. It's completely different. This is probably how our car moves, at least when we do the measurements and the modeling. So it's a stepping motion over the surface. So the wheels, move. When you power it, it's stepping. This is the nano world. And if you don't believe me, I took a small movie from Harvard, how it now operates in your cells, how the movement in your cell works. So this is, if you drive a car on the highway in your cells, you put down the highway, you see? And when the car has gone by, the highway is detached, and when the next car comes, the new highway is established. It's all dynamic, and it's happening at a tremendous speed now in your cells. And you see, this is how it is transported, things in your cells. Can you imagine? It walks. Millions of these walkers make things moving in your cells, in your body. So, the first car actually was built, electric car, in 1835 by this professor, actually at the University of Groningen. I'm very proud of that. You can find this in our museum. He made a small tour around the medieval cathedral in the center of Groningen. It doesn't look much like an electric car. It took a while before we have a modern electric car. And I think most of us will drive in electric cars in the future. This is our car. You see this tiny powder? 1 billion times 1 billion identical electric cars. Our car manufacturing plant is not so bad, after all. I go to schools now a lot after this Nobel Prize I got in Stockholm. And you see me explaining left and right here to these elementary school kids. But then you get fantastic questions. Are there traffic jams with your cars at the nano scale? Beautiful questions, These are kids, 8, 9 years old. So we built now nano roads, and we built nano cars to move them on nano roads. This is what one of my students did recently. And so we built these roads and see how we can get them moving under normal conditions over such a road from A to B. Directional movement and transport. But I want to finish with one question today, if you allow me. I think I have a few minutes left. And that is, in the joy of learning of discovery, going for this question, I was asked the question often, can you move something in your body? And you remember probably the Fantastic Voyage of Asimov, this book, this movie, where they had this kind of spaceship that was shrunk to micrometer dimensions and then injected in the body, and it went to remove a blood clot or so in the brain of a scientist. And yes, we thought, let's make a submarine. So this is a nanotube, and the scientists here know that carbon nanotubes are extremely popular in physics and chemistry and material science. So we decorated these carbon nanotubes with enzymes, 2 enzymes, catalase and glucose oxidase, because we discussed a lot in the group what would be a good fuel in your body. And we settled then on glucose because we all know there is plenty of sugar. So can we make a kind of a submarine with sugar that propels autonomously without touching? And this is what we built. So the sugar is converted by these 2 enzymes. You generate oxygen, and we make a kind of a jet, a rocket type propulsion. Here it is. You see it moving? This is the nanotube with the enzymes. What you see here, these bubbles, these black dots, that's oxygen. We know that sugar is burned. You don't see a nanotube here, this single tube, because these tubes, they tend to aggregate, to form these tiny aggregates, these spiders. But what you see here moving is completely autonomous movement with sugar, it's burning sugar, and it autonomously moves. I don't have to touch. It's just sugar, water. Sugar, water. That's it. And if the sugar is gone, it stops, and when you add new sugar, it moves again. It looks extremely primitive, eh? When you see this, I feel like a baby who makes the first step. This is how it feels. But realize it moves autonomously. And now we learn how to move it from here to there and to transport things. So will we have nanorobots in the future? Is it science or science fiction? I would predict, not today, not tomorrow, not in 10 years, but in 50 years from now, the doctors will inject a tiny robot in your blood vein, and it will go for a defect cell, deliver a drug, precise, or do a repair. 50 years from now, surgeons will be injected in your blood vein. Nanorobots or micro-robots. Yes, it will become reality, I think. We can make the first tiny steps. It's very primitive, but think of the Wright brothers. I'm not very good in prediction. I'm a scientist, you know. So I want to use this quote: the best way to predict the future is to invent it. And this is what we do together with our students, with our young talents. So we make indeed things moving. We can make nanocars. I showed you this here, this spider. We can make tubes that bend, micro droplets, rotating rods, particles. This is all autonomous movement. Rotatory, translational movement, bending, all based upon molecular designs. So yes, we can make things moving at the nanoscale. Again, the beginning. So I discussed with you today, starting with life, with the bird, for instance, or the things in your body, the machines, how to make dynamic systems that are out of equilibrium, that move. Trigger, response, motion. So yes, we can maybe think about smart drugs for precision therapeutics, or making tiny robots. Robotics will be a big area in the future. We all have to deal with robots in the coming 20, 30 years. Or making tiny molecular machines that do all kinds of functions. But I couldn't have done anything, wasn't it, for all my talented students that help, that work with us in the laboratory, that put their passion, their creativity, and their hard work to make this all possible. Because we have a lot of failures, and I didn't discuss much about the failures, but I mentioned occasionally that it took us 8 or 10 years to realize something. Let me remind you, this nano car, I told the students, you are not going to Australia, but you can build a nano car and then you can go to a conference in Australia. Now, a PhD in Holland is 4 years. It took us 8 years to realize it, so the first generation PhD student never made it to Australia. I'm sorry for them, because they work very hard. But the second generation students accomplished that. So they are my heroes. And together we try to invent our future. I want to give a small message for the young people, because how I experienced my career. I would say discover your talent. And most important, follow your dreams. All the young people are extremely talented and they have their dreams. And please, follow your dreams. This is a bit what I did. I would have never thought that I would have ended up in Stockholm. But I got a real passion for science. Be confident, because it goes often wrong. Science is about uncertainty. about the unknown. And often things go wrong because you are in the wrong path. And discover your energy. What is your passion? What gives you a lot of energy when you have a great feeling in the evening? And also discover your limits. Don't always take the easiest way. How high can you set your bar? How high can you jump? And that gives a great feeling, I tell you. But most and above all, to go in this adventure in the unknown, what is called the world of knowledge and science, follow your dreams. And if you think there's nothing to discover, because people sometimes say, everything has been discovered. I hope I convince you today we are just at the beginning. 20 years from now, you will look at your smartphone and say, what old-fashioned technology was that? Let me take this quote of Francis Bacon. There are ill-discoverers that think there is no land when they can see nothing but sea. And of course, we are facing our future quite a few serious issues where we need scientists, engineering, societal organizations, humanities, everybody. How to reduce CO2 emission to make a sustainable society. How to recycle our materials, I mentioned already. How to feed 10 billion people. How to fly without kerosene. These are not easy questions and need the joint effort of all scientists and the whole society to make that possible for the future. Then my final question, which I often get, did you know that you would get a Nobel Prize? And I said, come on guys. I was working as a teacher at the university. I was teaching to students. I was doing research with my research team, working on all these problems. I was involved in science organizations, etc. I mean, my answer to the journalist is always, if you want to win a medal at the Olympics next year in Tokyo, you know what these people do? These sports people? They get up at 5 o'clock, work damned hard, train like hell. And if you are then talented and you have a bit of luck, because that's also needed, you might win a medal next year in Tokyo. We work as scientists with our colleagues, our students, etc. That's our duty. But then I got a call from America in 2011. I will never forget, on a Tuesday evening, 9:15, when a colleague said, Ben, you were on American television last night. And I said, come on, you're kidding. No, he said, you were on American television in The Simpsons. Look, Simpsons 2011. And it said that was a week before the Nobel Prize announcement, and they had a betting pool. Chemistry, Richard Czar, Bill Murner, Ben Feringa, and Sona Kashira. Murner got the Nobel Prize in 2014. I had to wait another 2 years. The students came with this the next morning, and they said, isn't it great you were on The Simpsons? I said, yes. I said, if this is the highest honor that I ever get in my scientific career, to be on prime time, American television, to get nominated by The Simpsons, I don't need any medal. I'm really happy. This is the most fantastic thing that can happen. I had to wait another 2 years, and I got to the Swedish royal family to get this. It was a fairy tale. It's a dream for every boy or girl that enters into the field of science, of course. I want to finish today, once again, with one of my heroes from the past. 500 years ago, Leonardo da Vinci said, where nature finishes producing its own species, man begins, with the help of nature, to create an infinity of species. And for the young stars here, the students in the audience, who are going to discover our future, imagine the unimaginable. With that, I would like to thank the Academy, Novo Nordisk, again for the invitation, and thank you very much for your attention. Thank you so much.